Hey, so we are live. Make sure this thing works. Back to Twitch channel. Can I hear myself? Okay. Cool. That's working. Let's update. Edit this one. Running computer science. So we're on SBD day 2. Systematic program design day 2. Let's do that. I think everything else is fine. Yeah, okay, looks done. Okay, cool. Alright, let's start. Okay, well, that sounds fine. So, where were we yesterday? I think we did 1A and 1B. That's what we finished. Part 1 is... Oh, I need to log in here. Oh, man, okay. Sign in. Oh, okay, why does it do that? Alright, so... yeah, so now... Okay, we did how to design functions and the way that worked. How should we do it? Okay, Dr. Racket. Okay. On the screen, hang on, stream summary. Don't know how this works. Stream manager, I think is what I need. It's looking nice. Okay. Okay, alright, it's cool. I think we just leave that in there. Unstable though. Why is the bitrate too high? So we'll see if the bitrate causes any issues. 7.4. Maybe let's just make it we'll leave it as that and see how it goes. Alright, so open notes. New notes, yeah, that is the one. So yesterday we kind of got familiar with how to design function recipe, which basically needs signature, purpose, tests, stub, and a template, and that kind of comes from here, right? How to design function. Here's the design method. So kind of do it like that, which is cool. Double some check expects. I'm trying to remember what I learned yesterday. Yeah, so use the in the expect, trying to make a simple way this can be computed to true or false. Like here, 2 and 3 will give us 6. So this assumes like, hey, we know the height and width, and just expect. Because the image is 2 or 3, so the area of that would be 2 times 3. So doing it like that. Yeah, okay, that's fine. Alright, cool. So let's carry on today then from how to design data. Again, like some of these will show that I've already gone through before, which I have, like last year, and I stopped. So let's see if we can compress these 8 hours in like 2 hours. Because again, we've done it before. So will it capture the audio from my here? Okay, so you guys can listen. I think I'm gonna have to do this thing here. Okay. And then move. Move this there. So So I can go full screen the video, what we watched through. Okay.
That result. And that's kind of
7 minutes, but we'll double speed it.
this week we're going to talk about the design of data. And what we're going to see
Nick, hey, what's up, man?
really turns out to be a point of leverage in designing programs. Because when we design data, we make decisions
It's been
about
so
all the
long.
things
Like
that they operate
you're
with data.
the
Before we get to that, this video covers common expressions.
KFC
They're new kinds of expression in
data
Racket.
scientist, I
It's gonna
think.
let us program
If I remember
functions
right.
where there's more than just two cases.
How's things, man?
I have the constarter.racket file open from the lecture page.
I think it's
Let's
KFC. It
look at
was
the
one
software.
of I
It
can't
starts by
remember. Is it
defining
KFC?
three constants called I1, I2, and I3.
I know it was
They're
one of
all
the
three
big
rectangles.
company
And
that.
let's see,
Sorry, I
one is
can't
10
remember.
wide and 20 high, and the I2 is
This
20 by
is
20,
literally
and
like
I3
6
is 20
years
by 10. So
ago.
these are three rectangles of
Used
shape.
to. Oh, cool,
Now
cool,
here's
cool.
function design.
Okay. I need to listen to this. But basically now we're going through OSSU. So now every day for I don't know however long it takes to go through this and learn the fundamentals of computer science. So if you're up for that, hang around, man. It's gonna be fun. We're using this language called Racket, which is these parentheses already throw me off. But yeah, it should be fun, man. Stick around. Yeah. So what are you up to now then? If you're not at KFC anymore, you moved on to bigger and better things. Right, I'm gonna listen to the thing and come back to the chat in a second.
I have the constarter.racket file open from the lecture page. Let's just look at this file quickly. It starts by defining three constants called I1, I2, and I3. And they're all three rectangles. And let's see, one is 10 wide and 20 high, and the I2 is 20 by 20, and I3 is 20 by 10. So these are three rectangles of different shapes. And now here's a function design, and the function consumes an image and produces a string. And let's see, it produces the shape of the image, one of tall, square, or wide. And these three examples / check expects really help me understand this function. If I ask for the aspect ratio of I1, I get tall, whereas for I2 I get squared, and for I3 I get wide. And reading through the rest of this, there's a stub and a template that are commented out. Now when we look at the definition of the function, what does it say? It says, well, if the height of the image is greater than the width of the image, then produce tall. That's this whole if there, and that's its question, and that's its true answer. On the other hand, let's see, its false answer is another if that asks if the image height and width are equal, produce square, otherwise produce wide. So this function design works, and if I run it, I'll get what I want. But there is something I'm not entirely happy about here. If you think about this function, there are really three cases, right? There's the tall case, the square case, and the wide case. And those three cases really feel like they're parallel to me. They feel like they're corresponding cases. Whereas when we implement them here with if, we end up having one case tall, which has two other cases square and wide kind of inside of it. And that doesn't feel quite right. It doesn't feel quite right to have one case with two inside of it as opposed to three parallel cases. So what we're going to learn in this video is a new mechanism called con. That's what's called a multi-armed conditional. And that is something we can use when we want to make an expression that has different behavior depending on the answer to predicates. But there's more than two different options. So here we go, let's do it to this one. Let me first show you a new trick. If I do sharp sign semicolon, that's going to comment out the entire, all of that stuff. It basically comments out from balanced parentheses to balanced parentheses. It's easier than putting a semicolon before each line. Now let's redo this function. I'll say define aspect ratio image. And what I have is three cases. So what I'm going to do is I'm going to write con. And then there's three cases, and each case has a question and an answer. And there's three of them. So I'll just copy that, like that. Oh, and I spelled the name of it
So
wrong.
kind of like case statements.
Now notice something here, which is that I'm using square brackets instead of round parentheses around the question and answer pair. That's just a convention to make the question and answer pairs stand out better, particularly when they get larger. Square brackets and round parentheses are really treated the same by Racket.
Bigger and
Square
better
brackets
things.
balance
Here we
each other,
are.
round
That's what
parentheses
we
balance
want.
each other. You could use round parentheses here, but square brackets just make
Are you
it
still
look better.
streaming too? I'll check
Now,
you
what's
out
the
after
question for the
this.
first case? Well, the question for the first case is
See
actually
what
right
you've been
here.
up to.
I'll take that, and I'll replace that question with it. And if that question is true, then what's the answer? Well, the answer is right here. Oh. And what's the question for the second case? Well, the question for the second case is right here. And the answer for the second case is right there. And then what's the question for the third case? Well, the third case is the last case. It's the in all other cases case. And so there's a special question that we can put there called else, which means if it wasn't the first one or the second one, just do this. And the answer for the last case is wide. Let me first run this to make sure I haven't made any mistakes. I haven't, and it's working. And so the way I want to read this is it says, gee, there's multiple conditions. If image height is greater than image width, then produce this result. Evaluate this expression and produce that result. If image height is equal to image width, evaluate this expression and produce that result. Otherwise, or else, evaluate that expression and produce that result. And that's kind of nice. What that gets me is multiple questions, kind of all at the same level of nesting, all at the same level.
That makes sense.
So con is a good
Man,
one to
the
use
syntax just
for
throws me
multiple
off.
case expressions when there's more than two cases. You can use if and nest them the way we have up here, but it tends to read more easily if you use con when there's more than two cases. Now we'll do the usual thing and look at the rules for forming a con expression. It's just open paren con, and then one or more question answer pairs, where each question answer pair is open bracket, a question expression, and then an answer expression and a closed bracket. And all of the question expressions have to produce a boolean, except the last question expression, which is allowed to be the special word else, which is going to mean if you get to this question answer pair, definitely produce this answer.
I'm just gonna make a note here. So it goes in whatever. Expression, question, answer. Each must be a boolean. The last one should be an else. So I might just basically shape is something like this. So we can do that. Cool. All right, let's move on. That makes sense. Oh yeah, I don't want to do that. We're just gonna go through the questions in a second.
Rules for con off to the right.
Yeah, my last stream was in October. 9 years, nice.
Example. So what I'm going to do is make a new tab, and here's my simpler example. And I'll do the usual thing about putting the evaluation rules for con off to the right here. And now let's get going. We start evaluating with the open paren con. So this is a con expression, and we have to use the rules for con. There are question answer pairs, so there's no error. And let's see, the first question right here is not a value, it's an expression. So we need to evaluate it. Well, let's see, evaluating it, it's open paren greater than, it's a call to a primitive, so we would use the call to a primitive rule.
Yeah, by the way, like, what I'm finding is like these first tutorials, I guess you'd call it, very simple, especially if you've coded. Like 5 years ago, this would be like blow my mind and be stuck here, but because I've done it before, this feels repetitive. But the course material says like it will start off slow, but get used to it and just understand the syntax and take the time, because it will pace up, and towards the end it'll get much more complex. So I'm typing all of these by hand. I think he said, I don't know if I took a note, basically said the way that they teach you here, it will make simple things hard right now, but it will make hard things simple later down the line. So I don't know, in a couple of weeks we'll find out like how effective this thing is.
Both operands are already values, so we can apply the primitive directly. So this greater than 1, 2 is going to
start
produce false.
typing.
So what we're going to do is replace the entire con with a con in which the first question is false. Now we start evaluating again. Open paren con, it's a con. Let's see, the first question is false, so that takes us to the if the first question is false rule. And what that rule wants us to do is drop the first question answer pair. So what we get now is a new con in which this first question answer pair is going to be deleted entirely. I'm going to do Command E now to get myself more room here. Okay, let's see, open paren con, there are question answer pairs. The first question is not a value, it's an expression. So I need to evaluate the first question and replace the question with its value. Well, we know how to do that now. That just gives me false again. Open paren con, there are question answer pairs. The first question is false. So again, it's the drop the first question rule. So we basically drop the first question. Open paren con, there are questions. The first question is not a value, it's an expression.
So it doesn't really have the else case in here.
That is now true. Open paren con, the first question is true. Now I replace the entire con with the first answer expression. Okay, let's see what I have now. I have a value I'm done evaluating. The key intuition is that the way the evaluation of con works is it evaluates the first question. If it's false, it drops that question answer pair and starts over. If the first question is true, then it replaces the entire con with the first answer. You can see here an interesting pattern, right? Which is the rule for con, the rule for function call, the rule for if. They all work the same way. They, in some sense, try to do their thing and then get out of the way. Right here in this last step with con, once we got to the answer, the con was gone. And that's the same thing that happened with function call. Once the body of the function is replaced in, the function call itself is gone. These style of evaluation rules work that way. The idea is to take care of the more sophisticated construct and then get it out of the program. Okay, here's another example for you to do stepping. It's a little bit more complicated. I apologize for all these stepping examples, but we know that they really help people in terms of mastering how the language works, and that really starts to help as the programs get more complicated.
Yeah, exactly what I said 2 minutes ago.
It'll be interactive so that you kind of work through it as you go.
Okay, cool. Question 2. I think at this point I should start doing some of the things in here. So I added it to, can't remember, I did it yesterday, I forgot already. Cool. No, I think it's different. Yeah, starters. So we're in week 2. Con expressions, con starter kit. Starter kit, it's starter racket, but yeah. Alright. Okay, this looks starting to look a bit more complex. But isn't this the same example he was like walking us through? Okay, some definitions. I've been copy pasting stuff into this bigger file just so we have like references. This is gonna be a problem if I do that. I1. So we're gonna cheat and just make it II. It's gonna be annoying as the file gets bigger, but whatever, we'll just worry about that later on. Does it run? Okay, cool. Alright, so what do we need to do here? Problem. Given the following definition, absolute value, I guess. If n is bigger than 0, and if n is less than 0, and times -1, otherwise 0. Hand step the execution of hand step it. So okay, yeah, all right, fine. This is like one of the things where like I kind of know what it's doing, but all right, let's just go for it. So how did he do it? I just want to see his format. Go back. I was just showing the con. Okay. Right. Okay. Cool. So that's starting point. So we're gonna have n is gonna be -3. Oh, it's really gonna be long. Okay. Cool. Copy. I don't think I want this in this code. So I'm gonna delete this. I'm gonna work this in the file because it doesn't make sense to have this work problem just like copy paste it. So we're gonna do it here and it's gonna throw it away, I guess. Okay. So it starts off with -3, and then so we want us to step through the code. Is -3 greater than 0? Is it no? It's not. So we get false. Okay, and then it'll move to the next one. Is that what it's doing? Okay, yeah. So that case is gone. Okay. Oh, right, that's fine. So -3, and kind of skipping a step. So I think this will work in two phases when you got two things. I'm not really sure. I'll just run in one, same thing. Is -3 less than things? So that's true. Right. Okay, and then actually let's just do that. Okay, so that's true. So that means now that is true, I should exit at this point. And really be -3 times 3 is -4. Is it 4? I don't know. My maths is terrible. Okay, so I want to run this code and see if that actually makes sense. This is all gonna freak out. Copy so I can run it. Sure. This is not defined. Oh. -3 times 3 is +3. Okay. Yeah, I think that makes sense. I don't think I need to do any more to that. Okay, so we got like more people here today. Is anybody else learning with me? I think I have a link. Do I have a link? I don't have a link. So we're going through this thing. If anybody wants to jam on, feel free. There's a thing. Yeah, I can't wait to get to the maths part because I haven't done maths in like 12 years. That's the last time I studied like in school. So there's like, so after we get through the core stuff, so we're on this right now, 13 weeks, we're on week 2, basically today. And then gonna go through those, and once that is done, then we get to the core math part. So like this stuff, I'm gonna need a bit of a refresher because it's been a while. Like I forgot that minus and minus gives you a positive, for example. Yeah, it'd be fun. Maybe we can get to this by like 2-3 months from now. I don't know how long this will take. I mean, it definitely won't. Well, I don't know. Maybe it will take 13 weeks, 11 weeks, 48 hours, or oh, never mind. That's per week, right? So like, I'm planning to do this every day, like at least 2 hours a day. So it should be faster. Yeah, it should be fun. Okay. Where are Okay, let's move on. Don't need this one anymore. Don't save. Okay. Question 5. Yeah, I'm skipping these questions and we'll just do the problem sets at the end. Next color. Okay, cool. Let's watch this one.
TL color. As you know,
and again, like if you're just joining and watching, I'm repeating myself. The reason some of these videos are going to show that I've watched it is because I have like a year and a half ago and then I just stopped. So I'm kind of restarting this one again. I think I got up to week 4 or week 3 and I stopped. So
week is about designing data. And as part of that, we're going to introduce a new kind of design element called the data definition. What I'm going to do in this video, though, is just talk about the problem that data definitions solve. And the way I'm going to do it is first show you how to design functions recipe solution, a complete function design. Look at a problem we have in understanding that, and then show you a complete data definition and talk about how it solves the problem. Then in the next video, we'll look at designing data definitions from scratch. So now suppose you're working on a program that somebody else wrote, and the program has to do with simulating traffic. So it's reasonable to expect in a program like that there's going to be code that has to do with traffic lights and cars and trucks and things like that. Now you're reading that program, and you come to this function definition, and you ask yourself, what does it do? Well, the name is kind of a hint. It seems to produce the next color. So maybe if you give it a color, it gives you another color. But it's just not really very clear from this. Now at this point, of course, you might say, well, look, the problem is that this person didn't follow the how to design functions recipe. Let's imagine that they did follow the how to design functions recipe. So here's the same function with the how to design functions recipe. There's the original function definition. And now we see that the function consumes a natural and produces a natural. And it produces the next color of a traffic light. But here's a question. The signature says the function consumes natural. So can I call it with 3? 3 is a natural number. But I don't see any examples other than 0, 1, or 2. And what do these examples mean anyways? I mean, the examples match the function, so they kind of tell me the function's probably right. But when I call next color with 0 and it gives me back a 2, what does that mean? Well, in order to understand this problem, we have to understand something very important about data in programs. In any program, we have what we call the problem domain. In this case, the problem domain has to do with traffic and simulation of traffic lights and cars and roads and things like that. And in the problem domain, we have information in the problem domain. In this case, we might have a piece of information like a certain light is red. But inside the program, we don't have red lights, we don't have green lights, we don't have lights at all inside the program. What we have inside the program is data. In this case, the natural number 0. And what's going on when we design a program like this is that we're playing a game where we represent information in the problem domain using data in the program. In this case, we represent the fact that some light might be red using the natural number 0. And the inverse of that relationship is that we can interpret the natural number 0. If we're told that this natural number is supposed to represent some information about a light, we can interpret it as meaning that the light is red. And now if I tell you this, if I tell you, hey, to represent a red light, you use 0, and if 0 is representing a light, it means it's red, then you can start to understand this program a bit more. You can look at it and you can say, well, if 0 is red, then I guess maybe 1 is yellow. But instead of giving you this information in a piecemeal way, what we're going to do is we're going to use something called a data definition. And the data definition is really going to tell us everything we need to know about how we represent information as data. So now let's look at a new version of this program, the third version of it, that uses a data definition. In this third version of the traffic program, we've divided the file into 2 parts. The first part is called data definitions, and the second part is called functions. And in the data definitions part, we have one data definition. I want to read this quickly now, and in future videos this week we'll talk about it in more detail. But the data definition starts out with a type comment that says there's a new type, TL color, and the way you form something of TL color is that it's either 0, 1, or 2. We'll have more elaborate type comments in the next video. And it says that if you have a piece of this data, you interpret it as follows. Something that's a TL color is the color of a traffic light, and 0 means red, 1 means yellow, and 2 means green. And this last part is a template for operating on TL color. And for now, just read it as saying, if you're designing a function that operates on TL color, then there's really 3 cases. There's one case where the color is 0, there's one case where the color is 1, and there's one case where the color is 2. And now you know all about TL color. Now if we scroll down a little bit into the functions part, here's a function. And the signature now says, hey, this function consumes a TL color, and it produces a TL color. And notice we've already answered one of our questions from before. This function can't consume a 4 or 3, because it can only consume a TL color. And the only thing a TL color can be, I can see by looking up here at the type comment, a TL color can only be a 0, 1, or 2. And this function can only produce a TL color, a 0, or 1, or 2. And now it's producing the next color of a traffic light. And now this function gets to be easier to understand. If I say next color of a 0, which means red, then that produces a 2, which means green. And that's right, after a light is red, it's green. The next color of a 1, which means yellow, is a 0, which means red. And a light also goes from green to yellow. And now the template, well, what's the template for this function? Well, the template came from TL color, because this function consumes a TL color, and what we're going to see for the next several weeks is that the template for a function is determined by the type of data it consumes. And this just says, well, if you consume a 0, in other words, a red light, produce a green light. If you consume a 1, in other words, a yellow light, produce a red light, and a green light goes to a yellow light. There's a couple of important things going on here. One is that this data definition tells me how to represent information as data and how to interpret data as information. This data definition has made this program much more meaningful. And this data definition has also greatly simplified the design of this function. Because the signature now says TL color to TL color, I know all sorts of things this function can't consume. It can't consume the number 3. And I also know how to read this function and understand what it's doing. So that's what data definitions are going to do for us. They're going to help us really understand the relationship between information and data.
Yep, that makes sense.
And how it can be interpreted as information.
First example of using recipe together. So I didn't really make note of that. Alright, let's just open up city name starter. V2. I wish you could open an entire folder in this IDE, but you cannot, so I have to manually like fetch the thing every time. So this is atomic, non-distinct. We don't want the solution, we just want the question. Oh, great, perfect. We can just pull in here and just work through it. Imagine you're designing a program that, among other things, has information about the names of cities in its problem domain. Names of cities. Okay. Design a data definition to represent the name of a city. I'm gonna watch the video because I don't know what the recipe was. How to design data, maybe. We'll just see if we can piece it together and then watch his implementation after that. Okay, so I remember this from previously. This system is interpretation. So time is a natural interpretation. Number of ticks. Define some constants here. Template rules. What's this? And then the template here. Okay, so among other things, it has information about the names of cities. Design a data definition to represent the name of the city. I don't know what it expects me to do. Let's just watch.
Recipe using also the data-driven templates recipe. Now we're going to work through an example of designing a data definition from scratch using the how to design data recipe and the accompanying data-driven templates recipe. It's going to be a simpler example than the traffic light example you saw earlier in the week. What we're going to do over the next couple of lessons is build up our skills to designing more complicated data definitions like that. What I've got is the city name starter from the HTTD module webpage, and it says imagine that I'm designing a program that, among other things, has information about the names of cities in its problem domain. Design a data definition to represent the name of a city. So the key first thing that we do when we design a data definition is to work out the form of the information we're trying to represent. And it might even be good to just write down a couple examples. Maybe I'll put a little comment box right here. And I'll write some examples. So one example city name is Vancouver, and another example city name is Boston, for example. And these are all information. And now the question is, how am I going to represent that? What I'm going to do is go to the course website, and I'm going to go to the design recipes page. And this again provides me an index into all the design recipes. And I'll go to the how to design data recipe. In this webpage, I won't go through in detail now. I'm just going to work through it by example. Review it on your own.
This is the part we're
It tells me
missing.
about the basic parts of every data definition. And I'll pick this up later and set it down off to the right when we're working with Dr. Racken. And the key thing it helps me do is decide what kind of data definition to use based on the form of the information that we need to represent. Now remember, we're trying to represent city names, things like Vancouver and Boston. And the thing about that information is that it's atomic. And what I mean by atomic is you can't take it apart into pieces that are still meaningfully part of the same problem domain. So yes, it's true, I can take the city name Boston apart into the letters B-O-S-T-O-N, but those aren't meaningfully part of a city name in the sense they're not like neighborhoods of the city or something like that. So this information is atomic. And the way we represent atomic information is with a type comment that looks like this. We simply have a new type name, and we say what underlying primitive atomic data is going to be represented as. So going back over here to Dr. Racket, I'm going to say city name is string. A good way to represent this information is using strings. So for example, if we do this, the data that represents the city name Vancouver is going to be the string Vancouver. And the data that represents the city name Boston is going to be the string Boston. So here's my type comment, city name is string, and now I need to provide an interpretation, so I type interp period. And for simple atomic data, the interpretation is often fairly simple, especially for a case like this. We're just going to say the name of a city. And now the next part of the data definition is something that we didn't see in the last example, and we'll talk about why that is more in a couple videos. But we want to provide some examples of how the data definition represents information. So what I'm going to do is I'm going to say define city name 1 is, well, one good example is Boston. And define city name 2, and another good example is Vancouver. Now, I'll be honest with you, providing examples of really simple data definitions like this doesn't do that much work. But again, we're learning the recipe now so that it'll help us more with more complicated examples. And fairly soon we'll have data definitions where examples really are going to help us understand the data definition better. So there's the examples. The next step of the recipe is to produce the template for this data definition. Now to produce the template, what I do, I go back to the course website and I go to the design recipes page and I get the data-driven templates rules.
I think the hardest thing is just like getting used to these things and actually typing the way you want, because I've never thought of, when I never learned it this way. But yeah, we'll just go through the repetition and see how that works out.
Data-driven templates recipe. And the way this works is it says for a given type name, the data-driven template looks like this. So what I do is I say define fun for city name. And we're going to be quite particular about the name of the template. Naming the template directly after the type name is going to turn out to help us quite a bit later on in the course. And I'll pick as a parameter name for this template CN. And now I've got to do something about the body here. What I'm also going to do is I'm going to write template rules used like this. And now looking back at the data-driven templates page, what I see is the way to produce the body is to follow the rules in this table. What I do is I go to the type comment, I look at the first word after is, so that's string, and then I start working in this table from there. Now, string is what's called an atomic non-distinct type. The best way to understand what non-distinct means is to wait for a couple more videos, and then we'll see what distinct examples are. But string is right here, so this is the row of the table that I'm going to use, and I'm not inside of a con. You'll see what it means to be inside a con, again, in a couple of videos. But for the body, I'm just going to say ... x, where x is the actual parameter name. So the body of this template is just going to be ... cm.
Okay.
And I'm also going to write here.
Like yesterday, we were just doing that all the time, ... n. So now he's giving us a bit more structure. Because I was like, what do I put here? Because I think that's what I put everywhere. ... Yeah, exactly. So now, like, what he's saying, depending on the template type, there's going to be different common types. Okay. How to design data. Simple atomic data definitions. How to design world. Okay, that'll be interesting. How did he get to that part? It was like a nice table with atomic, simple atomic. Maybe it's a different doc. This one doesn't have the same thing. I don't know. Okay.
The template rule that I used, and the rule that I used was the atomic non-distinct rule.
Yeah, like what?
Used where x is the.
Yeah, like this. So I'm on the wrong one. Type of data. Oh, just formatted differently. Okay. So in this case, it was a string because the name is city. So the template will be appropriate predicate. String question mark x, and then body is going to be there. All right. Okay. Cool.
X is the actual parameter name. So the body of this template is just going to be ... cm. And I'm also going to write here the template rule that I used. And the rule that I used was the atomic non-distinct rule. And I'm also going to write the part of the type comment that matched that rule, which in this case is string.
Yeah, okay, like, yeah, I don't know. This seems a bit overkill, but again, in the intro, he said, like, eventually this will make sense. So we're going to keep doing it. Atomic non-distinct, and type is a string.
Now I'm going to run this, and there's nothing really to run, but the key thing is I didn't get any errors. If, for example, I had made a mistake, like I left a parenthesis off there, then I would get an error right now, and I would fix this poorly formed template right now. So I'll fix this poorly formed template right now. And now I've got this running properly. And what I'll do is I'll comment out the template, because we're never actually going to call this template function. We're just going to copy it into later function designs. And I'll get rid of this now, this scratch work, because that's already really captured in the data definition. So there you go. I've completed a first data definition by following the how to design data recipe, using also the data-driven templates recipe. In the next video, we'll design a function that uses this data definition.
Okay, cool. So now we're going back to the function from yesterday. Yeah, I just want to watch him do it, and then we can follow the pattern and go through the problem sets.
Last time, I showed you how to use the how to design data recipe to design a simple data definition. In this video, what I'm going to do is show you how to use the how to design functions recipe to design a function that consumes data defined by your own data definition. So this will be a function that consumes what's called
So it's not going to use the city one? Best starter?
non-primitive data. In this case, it'll be a function that consumes the type city name. In this problem, we're asked to design a function based on having...
Oh, it is, okay.
So the problem says use the city name data definition below to design a function that produces true if the given city is the best in the world. And we're allowed to decide whatever best city we want. So what's going on here is that we know that city name itself...
Yeah, this part here. For the first part of this course, we want you to list the template rules used after each template. I think that's just repetition to like get it in my head. Eventually we can drop that off.
That's consumed by the function is going to be represented as a city name type here. So that lets us get started right away on our signature. This function is going to consume a city name. And let's see, we're producing true. So it's a yes-no question. We're representing it with a Boolean. So that's going to be produce a Boolean. Now what are we going to do here? Well, we produce true if the given city is the best in the world. We can start with this as a purpose. Produce, I'll just copy it. Let's see, the next step of the recipe is the stub. We'll call this function best question mark. Remember, there's a convention.
Like, who decides if it's the best city? That's funny. I guess he does. Produce true if the given city is the best in the world. So this thing is purpose, right? And this thing signature, I think.
Name of predicates, functions that produce a Boolean value should end in a question mark. So we'll say best of some cm, and for the stub I'll say false. I'll just label this as the stub. And now we can get on to the check expect. And when we design a function using a data definition, this is a good time to go back to the how to design data definitions webpage. Remember, I get to that webpage by first going to the design recipes page, and then going to how to design data. And then this is an atomic data definition, a simple atomic data definition, so I'll go there. And in this webpage, each kind of data definition has a section called guidance on examples and tests. And this gives us some hints about making check expects.
Yeah, that's another thing yesterday. Like, when I was doing the test, I was like, hey, what kind of test should I write? I mean, normally it'd be like obvious, right, based on what we want to do. But yesterday I was confused on which one was it? This one here is like, how many tests do I write? 3. Do I need to do more? So it looks like there's gonna be some kind of guidance on what to test in these, at least in the simple cases. So we'll see.
Or this particular kind of data definition. So whenever you design a function using a data definition, go to this part of the how to design data definitions webpage and get some of this guidance. For our purposes now, I'll tell you what it says as we keep working. Basically says that 1 or 2 examples are enough. And that also is true of a function that produces a Boolean value. If you have a function that produces a Boolean value, you should always have at least 2 examples, one that produces true and one that produces false. So let's see if I say check, expect.
Yeah, I mean, Boolean's true or false, you need to test both scenarios, right?
Best question mark. And now I need to give some city name, like let's say Boston. And is that the best city in the world? Well, remember, the prompt description said we were free to choose any best city we want. So I love Boston when I live there, but let me say that it's not the best city in the world.
I'm just going to copy him, whatever.
Imaginary city for the best
I've
city.
never been to Boston.
We'll use Hogsmeade as our best city in the world. Now that is the best city in the world.
Hogsmeade?
And probably this is a good time to make purpose more specific.
Ugh,
Say,
cannot type.
Produce true if the given city is Hogsmeade. Okay, so now I've got 2 tests and the stub. I should run. And I get that one of the 2 tests fail, but both tests actually managed to run. So that tells me that my tests are well formed. Both tests ran. So now we can keep going. Let me start by making the screen bigger again. So let's see, signature, purpose, stub, check expects. Now the template. Well, the way we get the template now is we're going to put a note here that says, took template from...
So what did he do? If the city is, okay, if the city is, I'm just going to say London. And this check expects basically tests. Okay, so if I remember from yesterday, so we have signature, purpose, test, stub. Now we need template. And I think he wants us to reference the thing, but I'm gonna do it. Should I follow it every, like, because I kind of know, I think. Define. But best city name, and I think because like string is just gonna be, no, it's gonna return a boolean, right? True or false. So it's not dot dot dot. Okay, this is where I need to see what the thing says. Boolean. Oh, same thing. Boolean question mark x, and the body will still have x. Okay, we'll just do that, I guess. I think.
City name, because this function consumes the city name. City name is a data definition that we design. So we're going to take the template right here. What I'm going to do is copy it.
It's already here. Oh man. Oh, okay. So like the data stuff, and then you can just use that. Like before, yesterday we were only doing this. So this came in like literally in the last 20 minutes. So you can just say took it from this template instead of the recipe guide or whatever. Took template from city name be in the data definition right here. So you can just copy it to.
I'll have this note about where I got it, and the first thing I got to do is remember to rename it. I'll rename it to best. And now here's the template. Now let's see what I do next. This is a function that has 2 cases, a false case and a true case. So a good first thing to do when you have a function that has 2 cases is to add an if to the template. So what I'm going to do is I'm going to copy the existing template. I'll put an if in here, and for both the question and the true and false answer, I'll put the copy of the template. This is a way now of telling me, listen, there's an if, and in order to fill out all these parts, ... cn is what you have to work with. Let's see, cn is the city name. So let's see, in one case, the city...
So if it's x true, if it's y, so string equals, I think it was. String, can't remember. String, whatever, equals. I don't remember. Like, yeah, we'll just watch. I think it's gonna do the same thing. I think it was like equals. Man, I don't. I wish I could just run the thing too. Yeah, let's just run it. So can I do equals ABC AB? Is that a thing? Equal. Okay, so if it's equal, we give it equal. All right. So what? Expects a number given ABC. Yeah, maybe that's not how you do string equals. Like, let's just watch the video.
name is Hogsmeade. Let's see.
Yeah, string equals question mark. Okay, not equals, but like string equals. All right. String equals question mark. City name. And then London. Then do true. Is that what it was?
If the city name is Hogsmeade, then this example right here tells me I should produce true. So that's true. And if the city name is not Hogsmeade, then this example and the purpose tell me I should produce false. So that's going to be false. Let me run it.
It's gonna need one more.
I forgot when I was up here to comment out this stub. There we go. Both tests passed. Now, let me make a couple points here. One is, did you notice that there was a point in the template where this was ... cn? And then I...
previously defined... That's what you just said, right? So we just do... comment out the stub. Okay, so a couple of things. String equals... and then the ... So even though the template has this, doesn't mean, I guess that's just placeholder. I'm curious once the data type changes from atomic to what this will look like and how that will take shape. Because this, to me, looks nothing like, or kind of, I guess, if you just think about multi-line stuff. Because I would expect this to have like if or con or something, some kind of shape of the body, but I guess the thing says just do that, so that's a bit off to me right now. But we'll move on.
did that and replaced it with true. This is an important thing about templates. Templates tell you everything you have available to work with.
You just said it. It shows you what you can use, but not what you must use. Yeah, exactly.
They don't tell you you have to use all of it. So oftentimes you'll be deleting things out of templates. Another point to make about this function is, let's think about this. This says if string equals cn Hogsmeade is true, produce true. Otherwise, if string equals cn Hogsmeade is false, produce false. When you follow a very structured approach to designing code, sometimes you produce code that's a little bit more cumbersome than it needs to be. This function could instead just be this.
Yeah.
Let me comment out this version of it and run it again, and now that's working too. But don't worry if you produce this version of the function. This is clear and it's well tested. It's just that if you ever find yourself writing if xxx true false, that's always the same as just xxx.
Okay, cool. Okay, I think this was a good one. Yeah, just getting used to this. So data definition for an icon is just an image. Interpretation is the image of an icon. Some constants. Here's the template define function for icon I. Icon. What's an icon? Icon is an image. What type of? It is a non-distinct. Okay, image is okay. That's what I was thinking of. Yeah, image is an atomic non-distinct. In that case, the body has that in the template. So it goes through here and there's some kind of function for icon. And the rule used. Yeah, okay. That makes sense. Data of, oh man, orthogonal words, okay.
I hope you're already beginning to see some of the power of working with a systematic design process.
Yes, I am.
One piece of that is that you always know what to do next. There's always the next step of the recipe. And that step of the recipe tells you what kind of thing you need to write and where you should be looking to figure out how to write it. So when it's time to write the examples, you know that you can look at the signature and the purpose to help you figure out what the examples need to be. You've also seen the benefit of producing uniformly structured code that's easy for other programmers to read, and code that has an appropriate number of tests. But in this next part, you're going to see the power of systematic design really start to step up. What's going to happen is that because the design method itself, in other words, the meta design in some sense, because the design method itself is structured so that the how to design functions recipe is orthogonal, which is kind of a $10 word for means mostly independent. Because the functions recipe and the data recipe are orthogonal, it means that as we learn more forms of data, the functions recipe is going to continue to work unchanged or mostly unchanged with those forms of data. So now we're going to begin to cover the ground a lot more quickly because of this property of the way the recipes are designed. In week 1, and particularly at the end of week 1, we learned about primitive data, including types like string, number, and image. And we learned how to design function recipe, and we used it to design functions like double, which consumed a number, and yell, which consumed a string, and area, which consumed a number, and image area, which consumed an image. And what started to happen this week is we started to learn about other forms of data, and in particular we learned about non-primitive data, data where there's a type that we design with the how to design data definitions recipe. And what we did in the last 2 videos was we learned about atomic non-primitive data, and we designed the type city name, and then we designed the best function that consumed a city name. And earlier...
Yeah, so the thing is, like, so I've been writing code for like almost 5 years now. I've never thought of something as atomic. Like enums, I've seen enums in Ruby, like enumeration, but I've never said it out loud as enumeration. So I think this will help me just get some base mental models, I guess, when I look at code. Yeah, I'm curious what the other data types are. And I don't think this will be specific to this, whatever this language is, Racket. It should apply to across any other programming that we're going to do. Yeah, we'll see.
In the week, you actually saw a preview of a form of data called enumerations, which we haven't explicitly covered yet. We'll do that shortly. But you saw another type called traffic light color and a function next color.
String, right?
And what's going to happen the rest of this week is we're going to learn about some other forms of data, including intervals,
distinct, interval, itemization. No idea what those mean.
enumerations, itemizations, and a special form called distinct. And we'll see examples of those types. And you'll be able to design functions that operate on them. As I said before, the HTDF recipe is largely orthogonal to the form of data. So HTDF works the same way with different forms of data. And what that means in this week is we're going to focus most of the lecture time on designing different kinds of data definitions. And we're going to have to spend much less time on designing functions that consume that data. In some sense, what's happening is we did this little piece of the y-axis, how to design functions, and now we're working out the x-axis. And all this space in the middle, the cross product of the 2 axes, comes very cheaply. We won't have to spend much lecture time talking about these kinds of functions. Instead, we spend most of the lecture time talking about forms of data, and designing these kinds of functions comes almost for free. And what's great is the power of having a design method in which the individual recipes are orthogonal to the form of data is only going to grow from there. Next week, we're mostly going to focus on 2 things. One new form of data, compound data. And also a recipe that helps us design interactive programs like games and animations and things like that. And again, because of this orthogonality, most of the lecture time will be on compound data and on how to design worlds recipe. And we'll do some examples in the cross product, some examples in the green box, but we won't have to do all of them in lecture, because once you know how to design worlds and once you know compound data, you can do anything in the blue, red, or green boxes. Beyond that, when we do lists and trees are complicated structures, but because of this orthogonality, again, they're going to be much easier to learn in this course than they are in some other courses. Orthogonality is always great in design.
I think it's going to get harder when we get to lists and trees, because I have no idea what they are. Like, no idea.
Orthogonality in the design of the actual design method. And it's giving us some wonderful properties.
I mean, I've heard of them and I kind of know what it is, because you kind of have to use them, but I never learned it.
We can learn HTDF and HTDW, and we can learn forms of data, and we get the cross product for free. That's going to be a big benefit in terms of using this method. And later on, of course, we'll see some other examples of where we work orthogonality into our own designs and get some similar benefits.
Oh, cool. All right, interval. Let's go through that one.
In this video, I'm going to talk about the next form of data definition.
Seed number starter. Let's pull this one up. Man, I hate having to do this for this. I wish there was a better way, but just gonna go through it this way. I think after this course, we can go back to using a normal IDE and not have to worry about this Dr. Racket. Interval, right? That's what we seed num. Yeah, okay. Starter. Great.
Which is called an interval. So this is really just an example of how to design data and data-driven templates problem. I've got the seat numbers.
All right, so think through. Imagine that you're designing a program to manage ticket sales for a theater. Also imagine that the theater is perfectly rectangular in shape. Okay, cool. Design a data definition to represent a seat number in a row where each row has 32 tickets. So we need the seat number, not the row number. Okay. each row has 32, but how? That's how wide it is. How? Maybe that's not what. Okay, can we do this as based on what we know? Let's just see if we can work something, and then we'll compare his solution. Okay, so start with a type. We'll be designing a program that manages ticket sales for theatre. Ticket sales. Imagine theatre is rectangular. Designer data definition represent a seat number. Okay, seat number is what we're defining the definition for. This is obviously going to be a number. Or is it? Yeah. Because they just want the seat number, they don't want the row number. Okay. So the interpretation is number of. What means the seat number? Number of. Like name of the city. City name. I mean, number of the seat. I guess. I don't know. 32. And then some examples. Okay, so define seat number 1. Let's say 5. Am I understanding this thing right? Say, I don't know, like 15. Seat number in a row where the row has 32. Okay, I think, I don't know. I think this is how I would do it. I don't really know. I can't think of, because it doesn't want the row, right? It just wants seats. So if there's like, I don't know, if you can fit 32 times whatever seats, each thing's going to be unique, so I don't think 5 should do the thing. And then some kind of template. So in this case, let's look at the thing. So he said number. Okay, defines seed num. No, it's like function for seed num. In a row. Seat number for row? Is that actually what it's asking? So he wants a row here? Yeah, okay. I don't quite get the question, but okay. Define. This is how I would do it. I think I'm understanding the question. Given a row, give me the seat number. I think. Oh, I don't know. What else? And then after that, templates used. It's number, and then designing the function. Okay, I want to see if I got this right.
Starter file open, and because this is a how to design data problem, I'm going to put the how to design data definitions recipe here off to the right. And over in my browser window, I've got the how to design data recipe page open. Back at the problem, so imagine that we're designing a program to manage ticket sales for a theater, and we want to represent the seat number in a row, and each row has 32 seats, so it's kind of a boring theater. That's what this comment here means, that it's a perfectly rectangular theater, and we need to represent a seat number. So if you think about that, a row looks kind of like this, and the seat number is going to be something like 1 or 2 or 3, all the way up to 32. Since these are seat numbers and not indexes in a string, let's use the normal kind of numbers that people like, where they start at 1 and go to 32. So the question is, that's the information. The information is numbers from 1 to 32 that are going to be seat numbers. How are we going to represent that? Well, if we go over to the How to Design Data webpage, and again, this is a webpage that you should read ahead of time. I'm going to be using it kind of in a mode where I already know how to use it. But I'm going to scroll down to this table that says when the form of the information to be represented is atomic. Well, this is atomic. Seat numbers are going to be something like 1 or 2, and that's atomic. But I'm going to keep reading because sometimes there's something more specific. And here it is when it's numbers within a certain range. And that's exactly what this case is.
Yeah, I forgot that we're in the intervals. I just assumed it was a atomic. So I guess what does the interval look like? Design data interval. Oh, look at that. Okay. Constraint. Okay. It's limited to. Do we know what it's limited to? Each row has 32, but we don't know how many rows there are. Start, middle. Oh, does it mean? I mean, we know what is limited to within a row, and I guess the thing is, okay, never mind. We're just looking at just one row. Okay, cool. So, number of the seat in a specific row. So based on that, the constraint would be restricted to is between 1 and 32. Right, 32 seats. Seat number 1, seat number 15. Doesn't really care about start, middle, the end. I think we need that. Template rule. So now the rules can be different because an integer versus a number. Where was the number itemizations? Oh, okay, it's not none of those. It's not compound. So a interval doesn't really have a specific thing. So I guess interval is part of atomic non-distinct. So still be that, which makes sense. Okay. All right.
This case is it's numbers like 1, 2, 3, all the way up to 32. So it's numbers within a certain range. And there's a kind of data definition for that called an interval. So here we go to intervals. And now an interval type comment looks something like this. There's a type name, and then we're going to say a kind of number, and then a notation for talking about the range. Let me jump back over here to Dr. Racket and do it, and I'll talk about that notation as I go. So let's see, we're going to say something like seat num is, and then these are numbers, integers, between 1 and 32. And what's going on with these square brackets is the square brackets mean inclusive. So this means integers starting at 1, including 1, going up to 32, including 32. Let me just show you some variations on this so you'll understand all of what we can say. For one thing, this could be natural, because natural numbers are integers that start at 0. So I could say natural here. Natural 1 to 32, integer 1 to 32, they're the same. But some other variations, for example, if I said something like number 132, well, that's going to be a lot more things, because numbers include real numbers, like 1.3 and 1.4 and 1.5. We don't have that with C numbers. We really need naturals or integers here. If I said natural square bracket 1, comma, 32 round bracket, then that wouldn't include the 32, because the round bracket means up to but not including. So square means inclusive and round means non-inclusive. So there we go, there's our type comment. Now I've got to say, interpret this. So what's the interpretation here? Well, let's see. These are seat numbers in a row, and I might know some more information about that. In particular, what I might know is that 1 and 32 are aisle seats. Okay? Or I might know something else about the theater. But anything that would help me understand exactly what the numbers 1, 32, and all the numbers in between mean is what I would put in the interpretation. Now let me make some examples. I'll say seat number 1, and I'll just call that 1. And seat number 2 might be 12. And seat number 3 might be 32. And the reason I'm going to do multiple examples in this case, sometimes it's nice to have examples that illustrate specific things. So this might be an aisle, and this is a middle. And this is an aisle, for example. You always want to have at least one example, and you should have other examples if they're illustrative. And again, as I said when we were doing the city name data definition, as data definitions become richer, examples will become more important and more useful. So we've got the type comment, the interpretation, and the examples. Now we have to do the template. So I'll start the template like this: define fun for seat num. And there's going to be some body there. And I'll also start the template process like this by saying template rules used. And now I'm set to do the template. I'll go back over here to the data definition page. I'll follow this link to the data-driven templates page. And now I've got to look down and find this form of data. And intervals are atomic non-distinct. So we're going to end up using the same template rule here that we used for city name. Which is just
okay, what interval number? So that wasn't there, was it? Did I miss it? Yeah, this doesn't have it. So I must have the different documentation, something.
Parameter name. So we go back here.
Function for seat num. Yeah, this was an overkill. Didn't need to know that. Seat num. Okay.
Say we say open paren dot 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 the parameter name, which is seat num, and here we say atomic, non-distinct, and I always like to put after the colon here exactly what part of the type comment it was. Allows us to do that. You'll see starting in the next data definition we do, when data definitions get more complicated, why we're doing that. There we go. That data definition is complete. I'm going
to... Okay. Natural... Copy pasting that thing over. Okay, cool.
Run it now, just make sure everything's well formed. I didn't get any errors, so everything is well formed. I'll put a comment like that there, and we're good to go.
Okay, does he actually do the second part? So he just moves on to enumeration. So I guess in this section we just want to know how to define data for different data types, right? So initially it was atomic. I mean, it's still atomic non-distinct, but this one was a string. Well, you just do it like that. This one is an interval, so it's something like this. Yeah, but did he do a constraint? Okay. Next one is enumeration letter grade starter. Let's open that one up. Enumeration. Okay. Good evening. What is system design? System design. Did I type system design in the description? I'm doing systematic program design. It's the name of the course. So I think I don't know if you can access the chat history, but I've got a link there for computer science. It's this repo that has open sourced curriculum, and it's meant to match a degree from like any like college, university, whatever. And the courses are part of the, I think you call it the MOOCs, Massive Open Online Course or something. So we're going through that as part of the core CS right now. Systematic program design is one of them. And it's teaching you systematically how to design programs. But basically is what it is. Yeah. So now we're on enumeration. And like right now I'm learning through different types of data and how to design the data. So what he gives you is this structure and how to do it. So how to design function was the first thing yesterday, where like type is signature purpose, like this. What's the input, what's the output, what's the purpose of this function, write some tests, what do you expect. Here's a stub of how the function may look like, and then you get to writing the actual function out. Today we're looking at how to design data. So like before you get to this stage, let's define what this input data is, right? Or even the output data is. That's what we're looking at right now. So far we've done string and interval. So right now I'm working on enumeration. Let's copy paste over this one, right? And I guess like tomorrow, maybe day after tomorrow, we'll get to how to design worlds, where it starts combining these two fundamentals, I guess. I already see some recursion and stuff coming. That's gonna be they're gonna be fun. It's gonna be a head scratcher, but that's what I'm doing. I see the link. Okay, cool. Sounds like someone I should learn, or something you should learn. Yeah, 100%. Learn it with me. Open it up. Start typing, man. Well, I mean, I don't know if you're a man, but like, start typing. Okay, letter grade starter. Let's see what is that. As part of designing a system to keep track of student grades, you're asked to design a data definition to represent the letter grade in a course, which is A, B, or C. Okay, so enumeration is like you have a limited set of possible options, I guess. Yeah, is one of A, B, or C. Interpretation is a letter grade in a course. Examples are redundant. Okay, so for enumerations, you don't need to give examples like that, because it's either going to be A, B, or C. Here's the template. Function for letter grade LG, letter grade. If string equals A, da da da. And I guess this thing comes because it's an atomic distinct A, and A being a string, right? Is that what it was? Simple atomic. Okay, this is very. What's confusing me is just like going through this documentation. I need to find a better. I know there's another one where it's not this simple HTML is hyperlinked. How to design data? Is it enumeration? No, that's not what I'm looking for. Where is it? Should I scroll? Here, okay. So this is going to be atomic distinct, and this is string, and that's going to end up with this as the template body. Temporals used. I mean, he's already done the thing, right? So I don't know. Oh no. I know what I did wrong. I opened the solution. Okay. Never mind. I think so. I'll just explain what it's doing. We should have done this, but I think he's just going to explain that to us now. Let's see how much I got wrong.
In this case, it's going to be for an enumeration. So the data definition that we produce will be similar to the traffic light color example from earlier in the week. This is the problem in letter grade starter.racket. And again, I know that this is a data design problem, so I've got the how to design data recipe here, and I've got the how to design data webpage open in my browser here. We're designing a system to keep track of student grades, and we need to design a data definition to represent the letter grade in a course, which is one of A, B, or C. Now the key thing about the information in this problem is that there's 3 distinct values. In other words, every letter grade is going to be either the distinct value A, or the distinct value B, or the distinct value C. It isn't like something where we might be keeping track of the numerical score in a course, which is a whole bunch of numbers. Here there's really a modest number of distinct values, A, B, or C. And when the problem domain information is like that, when it consists of a fixed number of distinct values, then there's a special kind of data definition to use for that called an enumeration. And the way an enumeration works is that we're going to use one of in the type comment this way. Now this is exactly like the traffic light data definition from earlier this week. So here we go. I'm going to say letter grade is one of. And now what I'm going to do is I'm going to talk about the data used to represent each of the distinct cases. And I'll use strings in this case. I'll say that these are the 3 distinct data values which are going to represent the 3 distinct information values. And when you do an enumeration, the interpretation tends to be relatively straightforward. In this case, you'll just say the letter grade in a course. But if you think back to that example we saw at the beginning of the week, if, for example, you had decided to use the 3 data values, maybe numbers like 0, 1, and 2, well, then your interpretation would be more substantive. Then your interpretation would have to say something like, 0 means A, 1 means B, 2 means C. So part of why the interpretation is simple in this case is because we're using strings to represent the 3 cases, and the strings still clearly say what the cases are. The other thing that happens in enumerations is that examples are kind of silly. I mean, if we tried to write examples for this, what would we write? We'd write something like define letter grade 1 is A, means A. Define letter grade 2 is B, means B. Define letter grade 3 is C, means C. It's kind of silly, right? It's ridiculous. Because it's an enumeration, there's only 3 values. We know what the examples are before we get to the example stage. So we don't even bother to write them. What we write here is we say examples are redundant for enumerations. And once we get a couple weeks farther in the course, you don't even have to write that. We want you to write it for now, just as a way of remembering that the example step existed. Now we're going to do the template. So define fun for letter grade, LG. There's going to be some body here. Template rules used. And here we go. I'll go back over to the how to design data webpage. Here we were. And I'll scroll up to find the link to the data-driven templates recipe. And here we go. So I need to look in this column for the first word after is. Now remember, the first word after is one of. So it's not any of these. There's a special rule for one of. And one-ofs are always enumerations, like this case is, or an itemization, which is the example we'll do after this. And now this says that the body is a con with 1 clause per subclass of the one-of. What does that mean? What's the subclass of the one-of? Well, what's going on here in this one-of is there's 3 cases, or 3 subclasses. This says every letter grade in the world is either in this class, or in this class. Every letter grade in the world is either an A, a B, or a C. So here we go. It says that we're going to make a con with 1 clause per subclass of the one-of. So let me just do that. I'm going to say con, and there's going to be 3 of these, because there's 3 there, so there'll be 3 here. And down here in my template rules, I'm going to put that we use the one-of rule, and that there are 3 cases. Now what happens? Well, now I've gotten past the one of, and the next thing I see is an A. The next thing I see, in fact, is the string A. So which template rule is that? Because what this says is that for each question and answer expression, I'm going to form it by following the rule in the question or answer column of this table for the corresponding case. So I'm going to this A, and I'm trying this row in this table. And A is an atomic distinct value. Now you understand what the distinct value rule that we were just
Oh, never mind. So I thought it was because it was string. It's an atomic, because our string's here, right? But a specific string is a distinct value. So I guess that's the difference. Is that we know it can't be any random string. It'll be like a distinct string.
There's a single value, the string A. So it's this case. And now you also understand what the con question column of this table was for. it says that in the question column we're going to put the appropriate predicate, which is a string equal in this case. So we'll go back over here, and we'll say string equal question mark.
Oh, okay, that's what I got wrong. So I was only focusing on this bit here, which is also wrong because it would have been dot 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 LG. Really, it's this entire thing here.
Letter grade to A. That's the question. And in the cond answer, we're going to put just dot dot dot. Then you might ask, why aren't we putting dot 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 letter grade? Well, two answers. One answer is the table told us to put just dot dot dot. It didn't tell us to put dot 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 in the name of the parameter. It told us to just put dot dot dot. But the question is, why does the table say that? Well, the table says that because in this case we know what LG is. LG is the string A. It'll always be the string A if we get to this cond answer. So we're not putting it there to make that more clear. And so the template rule that we used here was atomic distinct value. A. Now we go on to the next row. Well, the next row is the string B. So we can go back. Has two or more distinct values, A, B, and C.
Use enumeration of the domain consider two or more distinct values. Okay, yeah, that makes sense. Let's move on. If you're doing this with me, are you caught up? I can move on otherwise. Itemization. Okay. Okay. What is itemization? Okay. Week 2, itemization. We want the starter, not the solution. Alright, countdown. Consider designing the system for controlling a new Eve display. Design a data definition to represent the current state of the countdown. Itemization, okay, current state, which falls in one of 3. Oh, okay. So it's not distinct like this, because it could be A, B, or C. It could be. So if it's nothing, then it's not started. Like if it's 0, it's non-started. Or rather, if it's 10. 10 to 1, incomplete. So between 10 to 1, it could be, there's like 10 options, right? So in that case, it can't be distinct. Is that why it's itemization? I don't know. Let's follow this. So what we need is how to design data. Itemization is comprised of it tells you right here, comprised of 2 or more subclasses, at least one of which is not distinct. There we go. So 10 to 9. 10 to 1 won't be distinct. So in that case, it's this kind, and the template for it is like this. But okay, let's just start typing it, and then we'll compare the answers to how he does it. So bird, in our case, what are we doing? State. Countdown state. I don't know. The countdown state is one off. Not started. So it starts from 10. What's non-started? What is it? It's nothing. Countdown is nothing when it starts. Or does it start at 11? And then we just count down from 11 maybe? Oh, you can have a boolean in there. Yeah, false, I guess. Has it started? No, that's false. Okay, this is actually trickier than I initially thought. Okay, false probably. So this is going to be a interval. It's interval. What did they call it? Number. Natural. Let's do that. It's natural, and it can be between 1 and 10, or it can be controlling the thing. Complete. Guess true means complete. But can't really use true. If false is not started, then true would be started. 0, I guess, right? It's a number 0. That means it's complete. Man, I'm bad at this. I don't know how to define this. Okay, so define. Oh, I need to do an interpretation here. So false means countdown has not started. Number. Yeah, I guess I can say number. Yeah, it's fine. Number's fine. Number, but then number, nah. Because number could be like 1.2 or whatever. We're not doing like milliseconds. It's just seconds. False means countdown hasn't started. What else? Natural is the current second, I guess. And then you go 0 is complete. Or like 0 is, yeah, complete. Complete or like New Year's past, right? Something like that. That's interpretation, so some tests. Define B1 false, B2 3. Oh, this is like define the data type. Okay, cool. So like countdown state. I'm just gonna go CS. CS1 is false. CS2, let's say like, who knows, 3 seconds into it. Define 3 is gonna be 0, like that's the end. What else we got? And then we need a template rule. One off. Huh. So it's okay. How did we do it before? I don't remember seeing this. Just define, and then template types used like that. Okay, cool. Let's just do the same thing here. So define function, countdown function. Current state. State of display or something? I don't know. It's going to take CS, countdown state, define that. And I think this will be a cond as well. Condition. Guess there'll be three types of conditions. So I'm not following the recipe here. I think so. Why is it doing 2? False. Okay. Let's look at that optimization. Condition on question answer, question answer. That's what we did here, right? QA is what I'm. Okay, let's just do that. Do you know what this means? That we can have 0 here. So there's only 2 cases. Yeah, and then 0 just means complete. Anything Natural. Okay, that means 1 through 10 is still counting down. Is still counting down. Okay, so template types used then is going to be non-distinct. No. Boolean, yes. So what's a Boolean? Boolean is atomic non-distinct. Boolean, we have that, and that just means like true or false. Is it started or not started? False is not started, true is started. Yeah, okay, I think that makes sense. What's the other data type used? We have a interval, really, which is another non-distinct, right? Where does was it itemization? It's mixed data. Yeah, it is mixed data. So I guess it's just be itemization. It's a mix of Boolean and interval. Yeah, I mean, this is this is what I would say. Let's check the answer, right?
Get started. Now in the second
okay. See how close we got. That's the thing. Just gonna sit down. Whoa.
In this how to design data problem, the type comment is going to end up with a one-off, but not all of the subclasses are going to be single distinct values. So this is what's going to be called itemization, and it'll be the most complex form of data that we see this week. This is the problem in Countdown Starter. So what we're supposed to do here is design a data definition to represent the current state of a New Year's Eve countdown. So this is something like the countdown ball in Times Square. And we're asked to design a data definition for that. As always, when we design a data definition, the first thing is to clearly identify the information in the problem domain that we're trying to represent. And in this case, the problem statement makes that very clear to us. In particular, it makes it clear that the information falls into one of three categories. The countdown hasn't started, it's from 10 to 1 second before midnight, or it's complete. The previous problem we saw, the letter grade problem, also had three categories. And here the categories are different. This first one is kind of distinct. The countdown hasn't started, that's a clear distinct state. But in this second category, there's not a single distinct value there. There's 10, 9, 8, all the way to 1. So there's a number of different values there. And then in the third category, again, there's a distinct state there. The countdown is complete. So this isn't going to be an enumeration. This is going to be what's called an itemization, because there are two or more subclasses, at least one of which is not a single distinct value. The center one is not a single distinct value. So that's going to be an itemization. And again, after this video is over, I encourage you to go to the design recipe page, go to the how to design data page. This table will remind you that itemization is what you need to use in a case like this, and you can go and read about the itemizations. Do that carefully after this video is over. I'll work through the problem now. So let's see. We start with the type comment as always.
See, that was also different. Like his yeah, off stream I'm gonna spend some time trying to find the documentation, but like if you look at what he showed.
I'll work through the problem now.
Oh.
So let's see. We start with this video is over.
Template use, yeah, this did it have it, or am I just imagining it? How to design data, we want itemization. Yeah, it doesn't have well, it does, it's just in a different order. It must be like the previous course then, from the one he's used in the video.
It's over. I'll work through the problem now. So let's see. We start with the type comment as always. So we'll say that countdown is one of, and there's three subclasses. And now we have to decide for each subclass how we'll represent that, what data will represent that. Well, let's see, if the countdown hasn't yet started, that's kind of a distinct state. So we can use any piece of atomic distinct data to represent that. Let's just use false. Here we'll use the Boolean value false to represent the countdown hasn't yet started. Now in the second subclass,
okay, so he's actually
from 1 to 10 inclusive. And in the third case, we also need a distinct value there. And we'll just use the string in this case, complete. So now we've got three distinct subclasses that correspond to the three distinct kinds of
okay, that's actually fine. 1 to 10 complete is, I mean, complete is means countdown. That means QA. Really, we need another one. Templates, atomic Wait. But it's distinct. It has to be. String. I'm really not sure. Non-distinct. See, what's tripping me up right now is non-distinct. It has to be a distinct string. So is this the right? It's not. I remember looking at it earlier. So we have atomic distinct. I think that's what we want. Yeah. So distinct string. This can be any of them. This is also non-distinct. It can be either or. It can be true or false. Yeah, I think this is right. Okay, continue.
We'll do an interpretation here. And I'll use multiple lines for this interpretation. I'll say false means countdown has not yet started. Natural 1 to 10 means countdown is running and how many seconds left.
Okay, so
means countdown is over. And if you want to, you can indulge your inner Virgo and make things line up nicely. If you don't want to, you don't have to. There's the type comment and the interpretation. Now we need some examples. So we might say
actually lining it up does look better. Alright, let's do that. Means countdown hasn't started. Means it is yeah, much better actually. Okay.
Countdown 1 is, yeah, I'll put a false here. It's an atomic distinct, so in some sense you might find that example is not particularly
So ended was going to be complete
now,
now, right?
Countdown 2 is 10. And I can put a comment if I want. Just started running. Define countdown 3. Almost over. And define countdown 4. Complete. And that one's clear.
Okay. So he didn't do this part. But does he do it in the second video? Like he's doing a half of the stuff. There you go. I think it's going to complete it here. Okay, cool.
So there's my example. Now we'll set up to do the template. Define fun for countdown. C. There'll be some body. Template rules used.
Also, I like how he doesn't put state, he just put countdown. And then he just said fun for state or display, it's fun for countdown, I guess. Keep it simple. Makes sense.
So now we have to go find the first template rule used. And again, we always start by looking at the word right after is in the type comment. And that word is one of. So if we go find the template rules page, again, we can find that by following this link, the data-driven templates recipe link. The one of rule is the rule we're going to use because this is an itemization. The one of rule is also what we use for enumerations, so we know how it starts out. It's going to tell us to make a con with one clause per subclass of the one of. So I'll go back over to the code now.
Per subclass, we're going to have 3 of them.
3 subclasses, so there'll be 3 question-answer pairs.
Yeah.
And I'll say that the rule that I used was one of 3 cases.
Okay. Template types. Type is different. One of 3 cases. Okay.
Okay, so now I go to the first case. The first case is false. Well, false is an atomic distinct value. And I need a predicate for the question that tests for false. And it turns out there is a predicate that tests whether a value is exactly false. So back at the code, I could put that predicate in. I could say false question mark C. This is atomic distinct, so dot dot dot.
Okay. Alright, this is what I'm missing. So false C. Once it do that, okay, and it's atomic distinct. Yeah, I got this way wrong. Like template type is not itemization. Like template rule is one of because it's itemization, right? So atomic, and also Boolean is distinct because there is no true. It has to be false. And then for Boolean, you do that, okay.
Atomic distinct.
Yeah, atomic distinct right there.
Now for the second
always
subcase,
put balls.
see, this is an interval. So going back to the data templates page, for interval, I need an appropriate predicate. So this is a predicate that, for example, tells me is it a number between 1 and 10. But I have to be a little careful here. If I just make this predicate be and 1 is less than or equal to C, and C is less than or equal to 10, and let me just do the answer clause quickly so we'll have that out of the way. Since this is an atomic non-distinct, this would be dot 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 C. That might be what you write, but this particular itemization is called a mixed data itemization. It's a mixed data itemization because there's different kinds of data in it. Not all three clauses are numbers. The first clause, the data is a Boolean. The second clause is a number, and the third, it's a string. I have to be very careful here because if I call this template with C being the string,
this could be a complete,
this
right?
less than or equal right here, this less than or equal is going to blow up because you can't call less than or equal giving it a string as an argument. So because this is a mixed data itemization, we have to guard this less than or equal against being called with a value that isn't a number. And the way we're going to guard it is we're going to say, well, you're only this middle case if you're a number and you're a number between 1 and 10. So I'm going to add one more test to the and.
Right, okay.
Now,
so the template is looking more and more like the actual solution, okay. And if you're a number and your less than 1, no, greater than or equal to 1, or greater than or less than or equal to 10. Okay.
If I call fun for countdown with false, this template will go there. If I call fun for countdown with a number that's between 1 and 10, this template will go there. Now I've done the code properly, and I need to add the template rule that I used. Atomic, non-distinct, and it's this interval right here. I'll just copy it.
You got to think, man, this is going to get some time getting used to.
There's a note here that says
Just thinking through problems like this.
Itemizations and large enumerations. This is an itemization. So we're allowed to use else for the last question. What that means is, right here for this question, I'm allowed to put else. I don't have to put a question that tests whether C is actually the string complete. Let me do the answer quickly. This complete is an atomic distinct, so the answer is going to be that. Now let me talk about why I'm allowed to put this else here, and it's really important. In this course, if you have written a well-formed type comment like countdown, and you later say that a function consumes a countdown, then you can count on the function being called with a legal countdown. And so what that means is, when this template runs in some specific function, if C isn't false and C isn't a number between 1 and 10, then C is guaranteed to be the string complete. You don't have to actually test here whether C is the string complete. What we're saying is that having taken the trouble to do the type comment and having taken the trouble to specify...
So this is kind of like the type definitions, right? I've never used TypeScript. Is this basically what you do? Probably.
You can count on that being respected. The reason that's a reasonable thing to do in this course is in other programming languages that you'll use, there's a part of the programming language implementation called the compiler, which will actually enforce that rule to make sure that it's always true. So it's a reasonable rule for you to start counting on here. So now that I've done this last case, I do need to go and add my template rule used, which is atomic distinct, and it's this complete here.
Okay, yep.
So let's see, I'll run it to make sure everything's well formed. I don't get any errors, so it is well formed, and I will comment out that piece of it. Save the file, and now I've got the data definition for this countdown type.
SN1 was defined where? Seed number. Previously. Where else is it defined? Oh man. That's what it's meant to be. Okay, cool. Man, I'm getting a bit tired now. It's like 1 AM. I think I'm gonna call it a day for today. We'll continue tomorrow. So Ghetto, Bob, and Mullah, thanks for hanging out. See you guys tomorrow. How do I stop the stream? Stop streaming.